Hi, and welcome back. Next up, we've once again got Tim Gott joining us for Fundamental Turbocharging Systems. Let's all get charged up. See you then.
All right, here we are back again. This is pretty exciting, one right after another, just like this. All right, we're going to do a little bit of turbocharging information this time. Same as before, here's the contact information. If you didn't get it last time, there'll be another screen at the end that will show you that. Did this already. I think I can skip this because I think most of you probably carried over from the last one. We did this with the history. We did this with the brands. Let's go and get right into the actual program. Manuals, we know about RSF. We have what we call RSFs, and they are recommended service facility for all the turbocharger and any related products, you know, the valves, controls, things like that. The RSFs are better in some respects than dealing with us at the factory because we have an interesting situation. If you send something back to us for, say, warranty as a turbocharger, and say you got a leaky turbocharger, I will about guarantee you that it is not the turbocharger that's causing the problem. The only thing we're going to look at when we tear it down is we're going to make sure that the workmanship is correct and that the parts are correct. If they are, the turbocharger is not the culprit. The problem is once we tear it all down to do this assessment, we can't put it back together without overhauling or do something like that that meets what our authorization is. So we have the RSFs. And the RSFs can do all the work. They're authorized by us at the factory to do the work on these turbochargers. If they take something apart and find out there is a warranty issue, then they will contact us. We'll take it from there through them and take care of the warranty portion of it. If there's no warranty issue, then they will go back to you and they will charge you whatever it is for the tear down evaluation, whatever, you know, but at least you'll get the thing back with a tag that says you can actually run it. So they do have product liability insurance. They do warranty repairs evaluations. They do it in accordance with our manuals. As you know, we talked about before, they're doing everything in accordance with. They're usually pretty quick. They're a lot faster than we are in some cases, and it's just a pre-approved network of shops. Basically, these are shops right now. We have Quality Aircraft that's in Tulsa, which, in full disclosure, we own Quality Aircraft. They're an RSF, but they also are a sister company to Hearts and Engine Technologies. There's Aero Recip up in Canada, Approved Turbo that's down in Florida, and Main Turbo that's in Visalia, California. So you got various choices around the country depending where you are. All right, back to history again. You know how I love my history. This is 1905. This was the original patent of an exhaust gas-driven supercharger, exhaust gas-driven supercharger, i.e. turbocharger, right? Exhaust gas-driven supercharger. This is some of the history that went through it. I mean, you had in 1905, 10, 15, 1918. 1918, this Dr. Moss took a Liberty engine, was turbocharged. He wanted to prove a point. So he goes up to Pikes Peak and took it up the top of Pikes Peak, which is like 14,000 feet. And when he ran the engine, he was able to get 356 horsepower, which means that it was even a boosted engine, because not only could he maintain the ground sea level output of 350, he was able to increase it to 356, which made a boosted engine, which we'll describe in a little bit. This is one of the old airplanes that this Schroeder guy decided to go up and try and see how high he could get with it. 33,000 feet, pretty good. I mean, if I was in that thing, I'd have a hard time getting me 33,000 feet in it, but they decided that this was a good airplane to take because they believed it would be less likely to break up in the event of a long fall from altitude, you know, if something went wrong. So this guy did this, went to 33,000 feet, then turned right around. This McCready went to 40,800 in an open cockpit airplane. The outside air temperature up there was minus 69 degrees. If you look at that chart that's on there, I mean, when men were men. I don't know that might be a hard time finding somebody to do that nowadays. So that's a kind of a unique situation. Why do we turbocharge something? I mean, power diminishes with altitude. You know, we lose an inch of manifold pressure for every 1,000 feet, give or take. That references about 3 or 4 horsepower. You know, you'll lose a ton. You know, you're 35. What's a recip engine? Like 35% efficient. So you're losing 50% out the exhaust of that heat energy. So the goal of a turbocharger or the turbocharger system, I should say, is to convert that exhaust heat energy into usable manifold pressure. We can burn more fuel. That's always nice, you know, but it'd be a lot better if we can just take a little engine, put a turbocharger on. We make it think it's bigger than what it actually is. Can you take this to a fault? Yes. You know, you get people that tend to overdo it sometimes, and, you know, sometimes you can cause problems because of that. But, you know, that's kind of neither here nor there. 5 basic systems. You got turbocharger, you got a controller, wastegate, pressure relief valve, and an intercooler. Turbocharger is just a big air pump. Kind of expensive, but it basically is a big air pump. The controller is what they consider the system brains. Now, all of these controllers are what we call mechanical controllers. You know, they're not electronic or anything like that. Although the new IE2 engine that's like on the Tecnums, the big Tecnums, the twin-engine Tecnum, it does have controllers and that is controlled electronically. Wastegates, they're just a slave to the controller. Whatever the controller allows, how much oil the controller allows in, to, and from the wastegate determines the position of that wastegate valve. So if the controller shuts itself off, shuts off the control inside, you know, the plunger inside, then the wastegate, the oil is stopped at the wastegate because it can't get to the controller, and the wastegate goes all the way shut. If you open that back up, then the oil flows from the wastegate, and as it flows from the wastegate, then the wastegate opens. Simple as that. Pressure relief valve, very simple, just a safety valve on top. Intercooler basically is just used to increase the air density. Remember in the old days we had the intercoolers that, you know, that you could buy them for different airplanes. Turbocharger is the big air pump, right? Primary function is not to increase pressure. Think about it. Turbocharger does not increase pressure. It actually increases the density of the air. You want to make more air dense. So you want to take that same chunk of air that you have in this ball and you want to suck it down into this ball. And you want to do that because you're increasing the density of the air coming into the engine. That way we can go to altitude and the engine thinks it's at sea, but we're at 10, 12, 20,000 feet, whatever it might be. Cold side materials are always aluminum. Hot side materials are going to be Inconel or stainless steel. Runs about 1,650 degrees and, you know, up to like 125,000 RPM, depending on the size of the turbocharger itself. Different turbocharger models, a little CF, the little Ray J, the old Ray J is considered our CF series, and they're going to run, you know, 180 to 230. Then there's 3 different sizes of the Garrett style, TO4s, 6s, and 8s, and they just basically go up in horsepower and or cabin pressurization if you need the extra, like a sonic venturi on some of the Cessnas, you know, like the 421s, things like that, they use TH08. Basically, we have a couple different terminologies. Boost is what we were referencing earlier. Boost is when you're anything above sea level manifold pressure. So say at sea level, and you know, we know that that's 2992, what, 14.7, 1116 millibars, you know, those are your standard pressures. So if you're at a standard day, 70 degrees, standard pressure, and you can get more than, you know, 2992, then you have a boosted engine. So if we basically use 30 inches of manifold pressure as something to go by, then anything 31 to 45 would be considered a boosted engine at sea level, and anything that maintained that 30 inches up to altitude, and that's all it can do, would be considered a normalized engine. Normalized engines are great because basically they don't have to be built to accommodate the boosting. Because they're basically, the engine doesn't know that it's operating at altitude in the same parameters it would if it was on sea level. So there's not like you have extra, you know, heavy rod bolts, you got anything weird in it. It's just a plain old engine that has been normalized so it maintains that power up to altitude. Boosted engines are built as boosted engines, and they usually be a little heavier case rods, things like that. And then we have a couple of upper deck and manifold pressure. Upper deck is always considered from the output of the turbocharger compressor to the throttle metering device, whatever that might be. Continental is that air valve that's in there. Fuel injection, you know, if it's a RSA fuel injection, it's wherever the airflow comes across the throttle plate. Manifold pressure is considered from the throttle plate to the actual cylinder itself. Deal because some of the controllers, like a slope controller, say, the slope controller will take a measurement upper deck on one side and manifold pressure on the other side. And that is how it calculates the position of the poppet valve inside, which controls the amount of oil being released through the system, which positions the wastegate valve. So that's how it does its work. It takes these pressures and meshes them against each other. In the old days, if you think about the old manifold systems, I mean, they weren't very good. I mean, you could have a whole bunch of drop across the throttle plate, across that throttle plate. Nowadays, with like the TSI 550, the K engine that's in the Cirrus, it's like a half-inch drop. So sometimes it can be a little touchy getting all that set up, that the slope controller recognizes it's only a half-inch drop, and it recognizes when, what's going on to keep the system nice and pure. Garrett style, we're just going to talk about the Garrett style. We're going to leave the Ray J's out basically, but the Garrett style uses full floating bearings. They are plain aluminum bearings. They're not ball bearings. The interesting thing is these bearings rotate at approximately 1/3 to 1/2 the crankshaft speed. Crankshaft, that's not right. The turbine wheel assembly speed. So think about it. We said earlier, if the turbocharger say the turbocharger turns 90,000 RPM, that means that the bearings themselves are turning between, between like 30,000 and 45,000 RPM. So I would suggest that we keep good oil going to those bearings, because you flatten the side of that bearing and you will have a problem. Piston rings on the Garrett style, there's a piston ring on each side. You got one on the turbine side and you got one on the compressor side. Those piston rings are not oil retention rings. That's why all turbochargers will leak when you first install them, okay? That's the way it is. There's other things that can cause it to keep leaking, but they'll all leak a little bit to start with, because these rings are not made to keep oil inside the turbocharger. Now, what does keep the oil inside is you have gas pressure on the turbine side, gas pressure on the compressor side. That pushing in against these rings is what keeps the oil inside the center housing. But remember, it's not supposed to be in there anyway. You just have oil coming through for lubrication. That's it. Okay? So you shouldn't have oil leaking out of the turbo that way. But think about it. You always have positive pressure on the turbo side. You don't always have positive pressure on the intake side, because in the intake, when you have low manifold pressure, you've got a suction. So you've got suction pressure constantly trying to pull oil from that center section, which is why you've got to keep the oil scavenged out. But no matter what, if you take off the compressor side, like the upper deck side, it's very likely that you put your finger up there, you'll have like not a film of oil, but you'll feel the oiliness in there, because it's always going to suck a little bit out of there. It's just going to do that, and there's nothing wrong with that. You can't have a leak, but you feel that oil, just that film on the inside of the components themselves. And this is just a picture to give you an idea. There's your piston rings there, and they're basically where those blue and red arrows are, and they fit right up inside there. There it comes. The piston rings keep the air and exhaust pressure out of the center housing. If those air pressures go in, it contaminates the oil that's in the center housing, and that's not going to do you any good at all. Notice we have oil pressure coming in. Whatever the engine oil pressure is, 30, 60 PSI, something like that. Interesting point. Notice it's coming down from the top, and it goes into that. See where that oil area is. It's got them little yellow things that come down past there. That's where it goes down and lubes the actual shaft and the bearings themselves. Once it's done that, it's zero. You no longer have any pressure. You lose your oil pressure as it comes through and does its job. Think about it. You take a garden hose. If I take that garden hose and I don't have anything on the end of it, and we're not going to count the resistance of the hose itself, but if I have nothing on the end of it, I turn the water on, it goes whoop, and I got all this water coming out. Do I have any pressure? No. I only have flow. There's no pressure at that point. Pressure is determined by any downstream restriction. So if I take a nozzle and I put it on that garden hose, now I've created a downstream restriction. Now I would read pressure in the line itself. Exact same thing here. Oil comes in, goes through those yellow sections. Once it goes past and lubricates the turbine wheel shaft itself, when it drops into the bottom there, the better way to say it, the bottom area of that center housing, you have zero oil pressure, so it's just like stagnant. So we have a big oil drain on the bottom, and a small inlet on the top, because we want to make sure we get all that oil out of there. Otherwise, it will come out through the compressor side and the turbine wheel side. Okay, we got to get that out of there. So what do we add to it? We got ourselves a scavenge pump. So we put a scavenge pump downstream, and then that way it pulls the oil from that center housing, so there's never oil in the center housing itself. If you've got a check valve, you've got a leaky check valve or something like that, if it allows that oil to come up in that center housing and it comes up to the level of the shaft, you will come in the morning and you will find a puddle of oil underneath the airplane, because it will have all just, migrated out the shaft itself and out, and usually out the exhaust pipe and on down onto the floor itself. In the intake side, it's up in the intake. It's kind of like a puddle up inside there. All right. Basically, here's a turbocharger. No controls. I mean, this would never work, obviously. It's just one thing would beget another. Turbocharger's pressurizing it. You got more coming out. It would just blow itself up, basically, because you don't have any controls on the system. So that takes it back to our components again, right? So a turbo controller, wastegate, the PRV, and the intercoolers. Get rid of the turbocharger, we're now the controllers. All right, the controllers, remember, they're the brains of the system. Different types, you've seen all these on there. That just depends on what kind of airplane you actually have and how it's set up. We have APCs, and all they do is basically do maximum manifold pressure. That's all they're checking. VAPCs do maximum and part throttle. Density and differential is two different controllers on the same engine. You'll find them on like a Navajo, that type of thing. But you have two controllers on there. One, the density controls the maximum side. Differentials your part throttle operations. And then you have slope controllers that basically take the density and differential control and plunk them together into one assembly, which is a slope controller. And of course, that uses the upper deck and the manifold pressure like we talked about a minute ago. So then we have wastegate valves. We got to have that wastegate valve. We've got hydraulic, fixed, pop-up, mechanical, all kind of wastegate valves. Hydraulic is the one that's on the top of the picture there. That's probably the most standard one you're used to seeing. It's got a hydraulic actual cylinder on it, and that actuates a little butterfly valve. You can kind of just barely see on the bottom of it there. The fixed wastegate are what's on the old, like the old Senecas, some of the old Arrows. They had that little bypass that went around the turbocharger and had that like big screw thing in it. I figured it was loose. I just tightened that all the way down. To me, that was stupid to have that stupid thing loose in there. So after we blew the engine up and we had to replace that, then we decided we had to learn about the system a little better. Fixed wastegate systems can be touchy, because since the only thing controlling it is the pilot, you've got to watch your manifold pressure up and down, especially if you've got a cold, dense day. It's very easy to overboost one of these engines. The old Senecas had a stupid system on them. They actually had it set up so that the manifold pressure gauges, if any of you ever fly an old one, the manifold pressure gauges were down on the lower panel, and they put two little yellow lights right here at the eyebrow. So you're rolling down the runway and you go to those lights, and whoop, those lights that come on means, oh, okay, that's one, and you just kind of use those lights as your guide. Well, you've already overboosted the engine. So not a good way, not a good setup, so you kind of need to learn how to operate it. Poppet valves, the one on the bottom of the picture there, that's what's in the old, like the TSIO 520, the WB engines, the big old turbocharger on them, and the wastegate fits right down inside at that point. And mechanical ones are like the later 182s, not the later ones, maybe the first 182s that were turbocharged, and what they did is they had a mechanical connection to the throttle. So when you're pushing the throttle in, halfway in, you use your regular, normally aspirated engine, and when you pushed in further, you physically, mechanically closed the wastegate, which allowed the exhaust gases over the turbine speeds up, and you would get boost from that. So again, you had to be a bit careful on how they were operated, because where the hydraulic and poppet, and the poppet's no more than another type of hydraulic, they were more of an automatic system. The fixed and the mechanical, you had to watch out on those. Pressure relief valve is just what it says, a fail-safe valve in case you exceed the maximum manifold pressure limits of the engine. They're usually set, a couple inches above the maximum pressure, because it's not a control valve. It shouldn't be something that's controlling anything in the system. It should just pop off. So you'll call them called a pop-off valve. It should just pop off if the maximum manifold pressure is exceeded. You have a wastegate. The wastegate jams shut, and the manifold pressure is coming up. This thing would relieve that manifold pressure. But I'll tell you right now, if the wastegate jams shut and you have like a TIO 540 on a Navajo, nothing's going to stop it. It's basically going to overboost, and you will end up tearing the engine down. Intercoolers, this was something that came up years ago. There were a couple companies out there who were saying, hey, you can increase your power, you can increase your altitude, you can do this and that if you add this intercooler on. Well, really, in reality, you cannot increase the power on an engine. You can't do it. It's certified for 315 horsepower, let's say 300. It's certified for 300 horsepower. If you add components to that engine, unless you're going to recertify that engine, you can't say, well, it now makes 350 horsepower. You can't do that. But what I can say is that I can take that same 300 horsepower engine that used to be limited to 20,000 feet, now I can limit it to 25,000 feet. Because what it allows me to do is the turbocharger, right? It's just compressing air. It's increasing that density, so it's compressing air and ramming it into the engine. But if you're going to compress air, you're going to also make it hot. And if that engine air is hot going in those cylinders, I start to approach that stage of detonation, to where I've exceeded the pressure and or temperature limits of the fuel, and that air is so hot it just detonates, and the cylinder just fires on its own without the spark plug, without anything else. And if you've ever seen detonation cylinders, things like that, it just destroys the engine itself. So what they did was they had these intercoolers, and what that allowed was it cooled down the charge. So they would be after the turbocharger compressor outlet. The air would go through there, they would use ram air, outside air, to cool it, and it'd go on into the engine. So that was a way to cool that charge going down the cylinders, decrease the chance of detonation, or you could say increase the altitude operating. Because remember, the higher you go, the more air you're going to compress, because the air is getting less and less dense as you go up to altitude, and you need to crunch that back together and get those oxygen molecules all back together. Okay? So here's some components. This is where you find, this is on a Cirrus. This is where they would be located. Logically, the turbocharger is going to be in the exhaust system. I mean, I would hope so. That's where it kind of lives. And the wastegate's going to be pretty close to it because it's going to be bypassing, right? Wastegate is somebody that's bypassing exhaust or putting it over the turbocharger itself. In this case, it's a twin turbo. It's got one on the other side also. One wastegate, and it just basically controls the flow to those turbochargers for the exhaust. Intercooler, you can see where it is, kind of that flat piece right on top there. The control and the waste, let's do the pressure relief first. It's in the front there. Notice it's in the manifold side. So on that manifold side, it's set a couple inches above what the actual manifold pressure limit is. Then you have the controller. And notice it hanging on the back of the engine there. Sometimes they're mounted as, mounted hard mounted, but a lot of times they've got their straps and their fluid lines coming in, and they're just mounted so they can vibrate. You want the vibration, and you always mount them vertically because you need that vibration to keep that poppet valve moving properly. If you lay it on its side, now gravity affects it, kind of lays down on its side, and it may affect the actual operation itself. So you'll see all the controllers are always mounted in a vertical condition, and it's basically the vibrations to get rid of what they call hysteresis. All right. Things we're sensitive to: insufficient lubrication, contaminated lubricants, foreign object damage, extreme temperatures. All right. If you have insufficient lubrication, you will have this, and you'll have a turbine shaft that is blue, and it'll create enough stress, enough heat that it'll stress the metal and shaft itself. If you can see on the kind of the right-hand side toward the picture before you get to the actual wheel itself, see that shiny portion there? That's actually the bearing. The bearing has made metal, and the galling that's occurred has transferred metal from that bearing assembly to the shaft itself. That is because you've had insufficient lubrication. Insufficient lubrication for us is extremely easy to identify. So if you have a turbocharger that, it's going out, or in the first few hours or something like that, and we take a look at it, it's going to be pretty easy to determine that it was not properly lubricated, so it probably did not get the pre-lube it was supposed to get when you first started it, that type of thing. So, beware. Here's your bearings. This is what happens with the bearings. If you flatten a bearing out, remember, these bearings are turning, on that example we used was 30,000 to 45,000 RPM. Oil comes in and through and around that bearing, so it's actually floating in oil the whole time. If you flatten out one of these bearings, you go, instead of a nice, just turning true, you now get that orbital motion. It's when you get that, now that bearing is moving back and forth. That bearing back and forth, the shaft inside is bending. And when that shaft is bending, right? Now the housings, because they're very tight tolerance on the turbine wheels, compressor wheels, and the housing, their respective housings, now they contact the side of the housing. Now they take contact side of the housing, they lose material, they lose balance, they're bouncing back and forth, and basically the amount of time it took me to do that, you could very easily just snap the shaft right off, and now you have no turbocharger at all. Although, I gotta say that people send me pictures and they will say, just doing 100-hour on this airplane, and I pulled off the air filter and pulled off the inlet duct, and here's what I see. And it's all this damage that's on the compressor wheel itself, and nobody even knew it. Nobody even knew it till they did the inspection. And I mean, it's like if it's coming in that way, it's probably something came into it, which we're going to talk about that anyway. So it kind of goes back and forth. On the turbine side, it's not going to last long. If you have a turbine bearing that's bad, that the turbocharger itself is not going to last. We recommend 25 to 35 hours on oil changes. I mean, bottom line is this turbocharger is connected to the engine. The engine, we build the turbocharger for the engine manufacturer. So whatever, limitations he puts on it as far as oil changes and things like that, that's what we're going to recommend you use. We don't care what kind of oil goes in them. Although, recent years, because we've come up with all this really full synthetic oils and things like that, it's the jury's still out, because there's a very good possibility that the fully synthetic oils lubricate so well, they don't allow the varnish to build up on the shaft, and that varnish that builds up on the shaft and those piston rings we talked about a little bit ago, that's what helps prevent excuse me, some of this oil from coming out of the turbocharger. So it actually is a benefit to build up some, I call it varnish because I'm not allowed to call it anything else, some varnish on that shaft, and the full synthetics may not allow that to happen. So I think I'd be wary of the full synthetic oils. Foreign object damage, everything you see on here, I just kept adding it to as the presentation, as I was building the presentation. These are all things we found inside turbochargers. Bolt rocks, rivets, things like that. Of course, they just destroy things as they're going in. Abrasive material to sand the dirt, usually because you have bad air filter or something like that, or you've been running on the alternate air doors open because it's broken or something like that, and you're sucking a lot of air in that way instead of going through the filter. And of course, then you have shop rags that go through it once in a while. There's a broken exhaust valve, came down through the cylinder itself, came out of the cylinder, down the exhaust, and hit the turbocharger. And of course, at 90,000 RPM, that's actually very good shape considering it's turning that fast and that chunk of material comes down through there. Here's the compressor wheel. This would be like, this is the scenario I was just saying. Guy calls me up and says, look at this, and shows me a picture, and he's got this. This has to come from the inlet coming into the compressor side of the turbocharger. It didn't come backwards. It had to come this way. And the problem with this is the all that metal that's worn off there, all that balance is gone now, but it looks like it's pretty even all the way around, so it must have halfway kept its balance, because it doesn't look like it's even hitting on the compressor wheel itself. But the other problem is there's metal missing from that, if I'm not mistaken. Where'd it go? Where'd it go? We got to find out where that went. So you can't stop by just changing the turbocharger. You got to go upstream or downstream of the turbocharger, look at the intercooler, go into the system, bore stroke the cylinders, find out if any of this metal has made it all the way through the system and into the engine. You could start with this picture and end up with an engine teardown. So, this is not a good thing to see when you're pulling something apart. This is what you call sulfide. This is a rag. This happened out here at Montgomery Aviation. A friend of mine called me up 2 years ago and he said, we just ruined a turbocharger. And I said, well, why? How did you do that? This guy's been doing work for like 100 years. And basically what had happened was they had pulled the air filter off the engine. And when they pulled the air filter off, the mechanic took a rag and stuffed it inside there to prevent contaminants, right? That's what we want to do. So he put this rag in there to prevent the contaminants. Who knows? Went off to lunch, God knows what they did, whatever. But again, the tie-in wasn't very good because somebody else came back, put the air filter on, but did not take the rag out of there. It was on Navajo, so they fired this thing up, got done with whatever they were doing, fired this thing up, started bringing up the power, they brought the power, and everything went, and basically just lost the turbo. And what it did was it took that rag and sucked it right into that turbocharger, right into the compressor side there, got hung up in the wheels, and the wheel there, and you can see it will always bend the blades backwards if it's something like that, because it's hanging it up. Remember, that turbocharger is starting to spool up, and it's got the exhaust gas spooling it from the turbine side, and it got hung up in there, and the wheel's still trying to turn, but then unfortunately the rag's hung up in between it. So it basically just bent the wheels backwards. This is not repairable. Well, it's repairable. You get to replace the wheel and start over again, basically. But you can't bend those back. There are no repairs on compressor wheels. This is one that we had this happened a few years ago. This was a leaker. They basically, is this a leaking? I can't remember. But basically, they were having a problem with the turbocharger. It was on the oil side. Couldn't figure out what was going on. Took it apart. See that yellow cap in there? Yeah, that yellow cap ended up inside the turbocharger itself. And it was not, that's what it was. It was not allowing the oil to drain from the center housing properly because it's kind of in the way. And then what would happen is the oil was leaking the whole time. There's nothing we could do about it. Couldn't find it. And guess where that oil cap came from? That was a protective device that was put on the turbocharger by us. You put it in there to prevent oil or contamination to get into center housing. The theory is you're supposed to take that off before you put the inlet and outlet connections on the turbocharger. In this case, it didn't get taken off and ended up inside. Here's one, and this is when I use my pointer, but if you can visualize on this one, this is on the outlet side. Now remember, when we showed that one diagram earlier, we basically had, and we showed that there was, on the outlet was like 3 times larger than the inlet, okay? That 3 times larger is so the oil can get out of there, right? So on this one, if you can visualize, look dead center in that picture, and you can see a semicircle. And what this tells me that the gasket that was on this particular outlet fitting was the gasket for the inlet, because it had a smaller diameter hole for the oil coming into the turbocharger center housing as opposed to going out. And what this did, this restricted that flow coming out of the turbocharger, allowed the turbocharger, the center housing to fill up with oil, and they couldn't get the oil leaks to stop. It just kept pouring out. It kept running out of the turbocharger. A lot of blue smoke when they would try to run it. They'd shut it down. They just couldn't get the oil out of it, okay? So it was just an incorrect gasket. It was on the wrong side. All right, how about some just plain old general condition here. Now there's one of my favorite pictures. I got to get one of these days. And I probably told you guys this last time we did this turbocharger presentation years ago. I still have not found a really, really good turbocharger running that shows me what I want to show, which is that right there. When you're working on a turbocharger system, this is its operating environment. It's not when you've got the airplane there drinking a cup of coffee, looking at the engine saying, what do we do next? It's not that. This is when that turbocharger operates, and notice the color. That is just glowing red, so hot that it's even kind of a white, on the yellow on the top or upper part there. But look at the turbo itself. It's almost translucent, okay? So think of the temperatures that operating at. Then think of, I didn't take the time to torque the bolts. Or then think of, well, it was only a small crack. Okay, this is all exhaust system stuff. That's why you have to have a good sealed exhaust system with the integrity to handle these kind of temperatures when you're working on a turbocharged airplane. Think about it. You've got these guys who would fly at nighttime, and they look out there and they see that nice glow out there, and some go, ooh, well, that's good. You want to see that glow out there. We used to have a Hiller. It was a UH-12 SL4, a big old monster thing. It had like a vertical 350 horsepower Lycoming engine, turbocharged engine, so TIO 540 vertical. The thing was a monster turbocharger on the side of it. We could never give rides at night because this is what it looked like, and nobody would get the stupid thing. So, I mean, they just glow red, okay? Because when you're flying, this is what you're going to see. So you look out there, it's at night, and you see that exhaust pipe out there, and it is just glowing red. That's exactly what you want to see. That means the system's working properly. Just remember, torquing, cracks, integrity of the exhaust system, because all that's going to play into whether that glow keeps glowing red or goes kind of like a duller color. Actually, it was somebody that gave me this picture too, because he took a picture at night because he thought that was so cool. Okay, general condition still, shaft spring spin freely. You know, you've stuck your finger in these things and you kind of spin the turbocharger, and, you know, it'll turn from, it's like it spins, but, you know, you can just stick your finger in there and turn the compressor wheel and things like that. If you deal with any of the Ray J's will not do that. The Ray J's use a spring-loaded labyrinth seal that's on the compressor side, so it does have a resistance to it. When you clamp the housings together, it does have a slight resistance to it, so it's going to take a little bit to actually turn it. And I mentioned that only because it doesn't turn as free as the Garrett style does. That labyrinth, I guess that's how you say that, never was good, that labyrinth seal, it's like a carbon seal, so it does act as a true oil seal on the compressor side of that Ray J turbocharger. And story is that in the old days, Garrett actually tried it. They actually tried using that type of a seal on their turbochargers, and they just felt the performance and what they lost from it, it just wasn't worth it. So they just went back to the old style that we have, you know, even today. If you want to inspect this thing, get a flashlight. Look back inside there. You got to get to the back of that. These, you know, on the turbine side and on the exhaust, on the exhaust side and on the compressor side, you need to get back in there and see the back of those blades. The front blades, sure, on the compressor side, you can see damage if it's there, but you really want to see in the back. Think of that wheel we looked at a little bit ago that had that exhaust valve that came down through it, the exhaust valve remnant came down through it. It was on the back side of that blade. So where that arrow is, that blue arrow, you want to see back there. Okay, and you can see it. If you look at enough turbochargers and you look in there, you can pick out the back side of that. And if you look at enough of them, if you have one that's bad, you'll know it's bad. You'll know. And if not, you got to run a borescope up inside there, pull the turbo, reach up inside there, and just check it with a borescope. This is where you have the wheels. Obviously, they shouldn't contact the housing, but they do. If they contact the housing, you have two conditions that could have happened. One, you've got a bearing going out. And like we talked about earlier, that bearing's going out, and it's allowing that shaft to whip a bit, and it's causing those blades to hit. Or the turbine, the wheel itself, the turbine assembly has been oversped, turning faster than what it was supposed to turn. Again, wastegate issue, controller issue, something like that, caused it to overspeed. When it overspeeds, the blades themselves grow. It's called creep. Talk about it a lot with turbine engines. But it's the same thing on a turbocharger. These blades will creep, and what happens is as they get longer, then they contact the housing. When they contact the housing, you can see in the picture where it's rubbed on the housing itself, and it's rolled material on the compressor wheel. Okay, so you know it's just it's just something that happens with turbochargers in when they're oversped. Now, if you look at this thing, you can tell that. Notice the nut. It's on the center there. That nut is on the compressor side. The weld is on I'm going to get it here in a minute. The weld is on the exhaust side, on the turbine side. So the nut's on the compressor side for the compressor wheel. So this is on the compressor side. Odds are it's probably been oversped, if I had to guess. Something else while we're talking about that nut, we've actually changed the design of these turbochargers because, you know, in the old days, you torque that nut on and you're going in the clockwise direction, so it's torqued down, right? So what happens is, if something gets in the turbocharger and jams that inlet, like that rag, that type of thing, the wheel keeps trying to turn, right? It keeps trying to turn, but the nut loosens up to the point that we've actually had them where the turbo's failed, the nut has come right off the shaft and ends up in the intake system itself. So what we did is we have changed that design to where they are reverse threads now. So if you change the turbine wheel, you're going to get the new design, which means you've got to have the new nut and everything that goes along with it. And that will prevent that from happening. That's only been a couple old. No, that's brand new. That's like 2 or 3 years old. Bearing clearances, you have two clearances on the turbocharger to check. The first one is radial, second one is axial. Okay, let's go back to radial. You're checking the radial clearance. You're talking about the shaft going through the turbocharger, and basically what you're saying is you're going to take a hand and you're going to put it on the compressor wheel and you're going to put it on the turbine wheel. And what you're going to do is you're going to lift up and push down and lift up and push down. And you do it evenly with both hands. If you only do it with one hand, I go wobble, wobble, you're acting like you're on a teeter-totter then. And you don't want that. You have to have both up and both down. And then you're trying to find out how much radial clearance is there in this turbocharger shaft bearing, the whole bit that's inside there. And you can see from the numbers, you're not allowed a whole lot. You don't have too much in there. So, 3 to 6 thou is a normal. What I tell people is typically what's going to happen is they reach in there and they start moving up and it goes clank, 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 clank. It's no good. I mean, that pretty much covers it. If there's just a small amount of movement, you're going to be fine. If there's no movement, you become a prophet because you are not going to be able to tell this guy that he is going to have problems with this turbocharger in the future because he has so much contaminants, I'm going to use that word, built up in the bearing area and that type of thing on the shaft that when you're trying to move it, you can't even move it. And what will happen is it may still turn, but and when it heats up, it'll probably turn free, but that's not going to get better. And what's going to happen is it's going to get tighter and tighter, and eventually it's going to affect the performance of the turbocharger itself. Same thing with axial or end play. You're taking your hands and you're trying to move the wheels assembly in and out of the turbocharger, okay? And you've got the same small amount of play. Now, you can use a dial indicator on each one of these. You've got to have it's a regular dial indicator, but you got all these special hookups and to get it connected and move it and all that. In most cases, if you have to get to that degree to find out exactly what it is in the field, odds are you probably don't have a problem because you're going clink, 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 you're fine. If you go clank, 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 and clank, 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 that's no good. You don't need a dial indicator to tell you that you have more than 3 thou clearance. But what I tell you earlier, you're supposed to always use the manuals. So use the manuals and make sure you're always checking them properly. In accordance with the manual, put your dial indicator on it. Overtemp. Here's an overtemp condition. This was a great turbocharger to get because it was actually damaged. And you can see there the ends of the blades are chipped off there. And this is overtemp. Look at the turbocharger itself. I mean, even looks at it. It looks like it got hot at one time or another. It just looks that way. And this is obviously on the turbine side because that's the welded side. And notice I keep wanting to point at it. Notice how in the center of the picture, the weld portion is not round, right? So that's all welded around there. But for balance purposes, some of that gets ground off when they're balancing. Okay, here's some more overtemp conditions. I don't know, you can't see it too well, but right there where that arrow's pointing, that is the piston ring. That piston ring is welded into the turbine wheel assembly. So obviously it's not going to spring out against the housing. So basically there is nothing there to prevent any oil from coming out. So it's just going to pour oil out of this thing, but it's basically overtemp. Look at the shaft. You can see it on the shaft there. Look at the color of the shaft. Here's another one. This was in 60 hours and 15 months, and this poor gentleman was just beside himself of how this turbocharger, something wrong with this turbocharger. We pulled this thing apart, and this is what we found. Again, the arrow is pointing to the piston ring. Notice all the contaminants down inside there, okay? All that contamination basically jammed that piston ring up, and this is nothing more than contamination and shaft rust. This occurs because the airplane's not flying much. 15 months, he flew at 60 hours. Probably a lot of it, the airplane was sitting and it just rusted that shaft. So every time he started, he just ripped off a new section of rust and dumped it down inside there. Then it all heated up, and where the piston ring is, it just basically welded that piston ring right into the shaft itself. Notice the reference, Continental M71. That means it was this bulletin that they've got was written in 1971. This is common knowledge. This is not anything new. And basically what it talked about was new and low time turbochargers rusting due to lack of use. And the only way to get out of it is to use it. Build airplanes. Senecas had an issue with this way back when, not so much now. Probably because they're not building that many Senecas. But when they were building Senecas, they built them down in Vero Beach, and they would park them outside, just like, they build something, park it outside. And can you think of a better place to park something outside that you're concerned with rusting than in Florida on the coast? I mean, I can't hardly think of a better place to be. Because think about it, that turbocharger system is wide open like the exhaust system. So all that moisture air and that salt air is getting up inside there, and it just rusts everything. So basically they come up with a program, they have to run the engines, and they have to run them more than just a couple minutes, because we all know that's not good for it anyway. So they have to run try to get that oil circulating in there to keep a good oil coating on the shaft until they can run it for, the normal flight, 10 hours or get something like that on to build that varnish up. Once that varnish is built up, no problem anymore because it will protect the shaft. Here's an even earlier one. This was in 1969. This was actually written because of some of the normalized systems, like on the beaches, on the beach bonanzas. They had a normalized system on it. The guy gets down there, and the runner, whoop, 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 he goes and takes off. He's flying out, gets 5,000 feet, and no turbo. Just, it's dead in the water. There's nothing there. Comes back down in, the turbocharger is stuck. All right? What they come up with, Air Research, they came up with this bulletin written in 1969, and what it says is, I'll say it nicely, gently whack the turbine side with a hammer. If you can break it free and turn it, go fly it. And you are good to go. Because all you're doing is breaking that stuck turbocharger loose. Okay? Now, look at see if we count, that's 1, 2, 3, 4, that's like 5 paragraphs. Can you imagine today writing a service bulletin in 5 paragraphs? It takes 5 paragraphs just to do the disclaimers, right? Things have changed a lot since 1969, but that's still a legal bulletin. It's still a current document for that type of a situation. Excessive contamination, I don't know, is that excessive? To me, it looks like kind of is considered the burn. It probably is excessive. That's all environmental. It's just operational, environmental, lots of that salt air, moisture, all this crud builds up around through there. And of course, the components to that are this. There's your wastegate. Now, how could that possibly be doing anything? So this is probably one that was not performing too well, and they took it off, and obviously none of that stuff would be salvageable. Now here's one that I thought I would never see again. This happened years ago. It was on an Aerostar. Guy called up, and he was having trouble, and he couldn't get boost on one of the engines, and sure enough, he actually overhauled the engines. Put the same turbochargers back on, it was a twin turbo, put the same turbochargers back on, still same problem, couldn't get his boost. So we went through everything we could think of, and I told him, I said, do me a favor, just send them in, we'll take a look at them. But I said, before you send them in, send me a picture of the turbochargers. And the reason I did that is because when we have people send stuff in, you're supposed to take all the fittings and components and all the crap off them, right? So I wanted to verify he took everything off before he sent it in. He sent me this picture. What do you see wrong with this picture? Can you see the gap between the wheel itself and the housing? I mean, it's big enough to drive a truck through. So basically what was happening was he was able to compress air. Yeah, he was able to compress it, but only to say, I don't remember what the altitude was, but only to like 5,000 or 15,000 feet, and the thing would fall on his face. It was supposed to be able to certify to 25, but he could get to 15, and he just couldn't hardly get any more out of the turbocharger. That's because all the exhaust air was bypassing. It was just bypassing through here. That compressor wheel and housing were incorrect. I think it was the housing in this case that was incorrect. So I thought, man, that's tough. The guy, I mean, think about it. The guy overhauled the engine. So, you know, that's pretty sad. So then here, just several weeks ago, I had a guy call me up, same problem. So we went through all the normal troubleshooting, things like that, and I told him, I said, we need to check the housing and find out what housing's on that. I said, take me a picture. Guess what? So, clocking error, this is one the guy put the turbocharger on, and of course, when you get the turbocharger, you know, when you buy one as a replacement, it's boxed. How should I say? It's clocked so it can be boxed properly, packaged properly. You have to reset it. So like if you're buying one for a Cirrus, you're going to take the turbocharger, you loosen up the bolts that hold the housings snug, and then you bolt it to the exhaust side, get all that set, and then you rotate the center housing to where your hoses are correct, and you rotate the compressor housing, get everything all hooked up, snug everything down, take it back off, do all the torquing, do all your safeties, that type of thing, put it back on, bolt on. Well, this one apparently they took it apart the wrong way. And what they did was they unbolted the center section. And when they did that, then they rotated the turbocharger, and you can see where the threaded holes, and then you can see where it got shifted, and it got screwed down once, got screwed down twice, and there was no threaded insert there. And the reason they sent it in for warranty was because they could not get torque. Well, I hope not, and I'm really glad they couldn't. Because if that thing would have started and done anything, it would have come apart. So it's just one of those times it was an improper setup. And the guy came up to me at one of the shows. I thought, oh my Lord, this guy's going to hit me or something. But he told me, he said, it was my mistake. He said, one of my guys was doing it, I wasn't paying attention. Avoiding turbo oil leaks, we're about out of time here. Drain ports must be down, no sink traps, where you have oil being caught up, delamination of hoses, sludge in the bearing housing. Stick your finger up in there in that bearing housing, the center housing, and look. Line restrictions or faulty check valves. Probably the biggest thing we have a problem with right now is check valves. They're not checking, allowing oil to fill the center housing back up, and then, you're done. You have a lot of oil leakage. Overspeed, overshoot, overboost, just common terms of what happens to turbochargers. They turn too fast, or the automatic controls can't control them, or overboost. Inspections, normal, you would think you'd see. SAIB, this is on clamps. This is going to be another thing that the feds are going to be getting really tight on. These clamps are getting old and they're cracking. Cool down, this is one of those things that, I personally, you go by what the POH says, you've got 4 facts and 2 variables. 400 series need to be cooled down. 600 series are aluminum, which is the Ray J's, you do not need to cool them down. Boosted engines need to be cooled down. Normalized engines do not, because they haven't even been online for a while. Pilots and mechanics are some of the biggest abusers of it. There's our online videos. I think I showed you that last time. I thank you very much. There's the contact information, and by my count, I'm almost exactly right on time. So I want you all have a wonderful day. Hopefully we'll be able to get together next year and we'll be able to drink a beer and talk some more about airplane stuff. So thank you very much. Bye-bye.